In this video, we consider a second use of Turing machines, and this is to compute functions. So this video is about Turing machines for computing functions. Up to now, we have used Turing machines to accept words, to accept languages, and now we use it for computing functions. And that's actually one of the historic motivations for the Turing machines, to describe what can be computed. And let's start with this Turing machine. We have an initial state, and in this initial state we stay, and if we read an I, then we leave it like this, and we go to the left. So we go to the left until we reach a blank. Actually, there can only be one step to the left. So once we have reached the blank, we replace the blank with an I, and we don't move. And then we go to this final or accepting state. So what this Turing machine does is, if we have our infinite tape here, then we have blanks, and then we might have some I's or vertical bars, and then we have more blanks. And initially our head is on the leftmost symbol, and then we go one step to the left, so to this position, and then we replace this blank by another vertical bar or an I. And then we stop. Now, what does this Turing machine do? It actually adds one of the I's, or one vertical bar on the tape. So we can say that it computes a function, and this function is in fact an increment. So we can consider it as a function from the natural numbers to the natural numbers if we have an encoding in unary. So this would be a unary encoding. In general, a Turing machine computes, we can say that it computes a partial function. Partial function f from sigma star to sigma star. So there's some input on the tape, then we start the Turing machine, and at some point, if we are lucky, the Turing machine halts, and what we find on the tape then, that's the result of the computation. So Turing machine starts on input, if Turing machine halts, the computed value which would be f of x, is the string on the tape. And if the Turing machine does not halt, the function is undefined. If Tm does not halt, the function f is undefined for this input. And in this sense, the Turing machine can be used to compute a function. So actually, this function that's computed here is the function. We have a function f that takes a number of i's, let's say n, and the result is that we have one more. So this is actually an increment, or can be regarded as an increment using unary encoding. And in general, we can use the Turing machines also to compute functions from the natural numbers to the natural numbers. So TMs can also be used, to compute functions from the natural numbers to the natural numbers. However, here it is crucial that we have to choose an encoding. But we have to choose an encoding. Typical encoding would be unary, like this one, or for example binary. Unary, binary. You can also use decimal if you want, but that's more difficult to compute actually. And the encoding is crucial because of the for example, time or space requirements. For example, if we have a number that's encoded in unary, we need as many symbols as the number itself. So it's much more efficient to use, for example, binary encoding, where the length of the encoding is logarithmic to the number. But this will be important later on for time and space complexity.